Alright, so today we move on to rhombuses or rhombi, is another plural form, kites, and regular polygons, all of which use the same method. Now, there are special formulas for rhombuses and kites, there are special formulas for regular polygons, but let's be honest, you're not going to memorize those and hang on to those over the long haul, so there's no reason to even fool with them. So we're going to use one method for all of these. We're going to divide the figure into triangles, because all kites, all rhombuses, all polygons can be divided into triangles, and find the areas of the separate pieces. So we'll start with this first kite. We learned back in Unit 6 that kites have two pairs of congruent adjacent sides. So you have two sides the same length on the left of this one. On the right you have two longer sides of the same length. You have right angles where the diagonals meet, always in a kite, which means we have built-in bases and heights for all the triangles in the picture. Now, there's a couple different ways we can attack this. We could divide it in half and do the left half and the right half. Well, they're not technically halves, the left section and the right section, and treat those like isosceles triangles. Or we can divide it into a top scaling triangle and a bottom scaling triangle and find the area that way. It really doesn't matter which way we do it. So I'm just going to make a choice. I could also, if I want to do things the really longest way, I could find areas of the four separate right triangles in the picture and then add them all together. I don't want to work that hard, so I'm going to do two triangles. I'm going to divide them into the left half and the right half, or the left piece and the right piece. So in the left piece, I'm going to outline that in pink. That is an isosceles triangle. It has a base, if I turn it this way, it has a base of 3 plus 3 or 6 and a height of 4. So it has a built-in base and height because of the right angle where the diagonals meet. So I can apply the formula. Area equals half times the base of 6 times the height of 4. Half of 6 is 3. 3 times 4 is 12. So that section has an area of 12. Okay, quick and easy. Okay, the other section, I'm not sure if this color is different enough, we're going to try it. The other section I'm going to outline in purple. So this triangle has the same base as the first one did. 3 plus 3 is 6. All the way across the bottom of that triangle is 6. And its height is 9, much taller when you turn it this way. So the area is half times base, which is 6, times the height of 9. Half of 6 is 3. 3 times 9 is 27. So we're going to just piece it together. To get the total area, we want to add those pieces. So total area is area equals 12 plus 27, which is 39. We're meters squared on this one. No new formula is needed. Divide it into triangles. Now, another thought, another option, is to divide it into the top section and the bottom section. The nice thing about that is you have triangles that are 13 across the base and 3 high, and both of them are the same. So if you find the top section, you can just double it to get the bottom section added in. So that's a little bit faster. So however you see it, just chop it into triangles and roll with it. Okay, let's take a look at the next one. Okay, now I know it's a kite because it says in the instructions, compute the area of the kite below. Alright, so the way that it's turned, since I have equal pieces across the diagonal, 8 and 8, that means the top two sides are equal and the bottom two sides have to be equal. It's almost a rhombus. Pretty close. Okay, now I'm going to divide this one into the top triangle, or the top big section, and the bottom section. So I want to find the area of the entire top section. Alright, so area equals 1/2 times the base, so all the way across the bottom is 8 plus 8, which is 16, times the height, which makes the right angle at the base. Oh, oops, they didn't tell us that. Now what do we do? Well, it's a right triangle right here. See this right triangle, this piece right here? Pythagorean theorem says 8 squared plus something squared equals 10 squared, or blank 8, 10. Well, it turns out that that's a triple. 3, 4, 5, if you double it, is 6, 8, 10. 6, 8, 10 is one of those triples that we originally put in our notes on Pythagorean triples. That's one that pops up pretty often, and it's one that you should have memorized. So this is a height of 6 centimeters. Now the catch to not knowing your triples is that you would actually have to work it out. So if you didn't know that that was 6, you'd have to kind of find a place off to the side and do x squared plus 8 squared equals 10 squared. X squared plus 64 is 100. Subtract 64, x squared is 36. Take a square root, x equals 6. So you could solve for it, but if you just know your triple, you save yourself a lot of work. And I promise you, on the ACT, if there is a missing measurement that you need, there's a really good chance that it's going to be part of a Pythagorean triple. If you memorize those basic triples that I gave you in your notes, you're going to shave some time off. Okay, so the height is 6. Let's go back to the formula. So 1/2 times the base of 16 times the height of 6. Half of 16 is 8. 8 times 6 is 48. So the top half has an area of 48. Or the top section. It's not truly half. I keep saying that, but it's not really half. The bottom section, we'll change colors for this one. So this bottom section is upside down. So I can either turn the paper upside down and look at it. So if I look at it from this perspective, I have a triangle with a base of 16 again, but this one has a height of 7. I'm going to turn it back around so that it's not real crazy. So for the bottom part, we have area equals 1/2 times base of 16 times the height of 7. Half of 16 is 8. 8 times 7 is 56. Then to get the entire area, we're going to add the parts. So area equals 48 plus 56, which is 104 squared centimeters. Alright, looking on down the paper, we're going to see a couple of rhombuses. Rhombuses are nearly the same as kites, but they're better because you always get 2 equal pieces when you divide it in half. So you find 1/2 and you just double it to get the other half. So if this first figure is a rhombus, we know for certain because of the rules of rhombuses we learned back in chapter 6 that the diagonals make a right angle. We know that this little half of a diagonal is 25, which means the other half is 25 because rhombuses have diagonals that divide themselves or divide each other into equal pieces that bisect each other. So 22 for this diagonal part means 22 for the other half of that same diagonal. If I chop this up into 2 separate triangles, there's multiple ways to do that. You just pick one. So I'm going to turn it this way and look at it from this perspective. It's a diamond. And pick a half to work with. So I'm going to take the top half. The top half has a base of 22 plus 22, which is 44, and a height of 25. So the area of that is half times 44 times 25. Okay, well let's do that calculation. Half of 44 is 22, and here I might actually want to pull my calculator out because I don't want to do that by hand. 22 times 25 is 550. If you prefer to do 1/2 times 44 times 25, it's more work, but the calculator will do it. So 550 for half of the figure. Now, unlike the kite, this half is exactly the same. It's a mirror image of the other. So that's another 550. Let's not reinvent the wheel, just add two 550s, or 550 times 2 is faster. So 2 times 550 is 1,100 feet squared. Alright, let's do one more rhombus problem. Sometimes we don't get both diagonals. Sometimes they just give us one. So I think naturally this is already divided into two triangles that are workable. So we'll take the top half. This one is truly half the figure since it is a rhombus. All four sides are equal. I need the area of that. So area equals half times base of 16 times height. Now, I don't know the height. It didn't tell me. So let me draw that in and see if I can figure it out. Okay, the height is going to divide that triangle in half exactly, which means I have a half of the diagonal here at the bottom that's 8. Half of 16 is 8. 8 blank 17 is a Pythagorean triple that I have repeatedly urged you to memorize. If you don't know it, you need to do 8 squared plus height squared equals 17 squared and work it out. Or you can turn around and look on the back wall at the poster and find the 8 blank 17 and find out that the missing piece is 15 millimeters. 8, 15, 17 is a Pythagorean triple. You need to memorize it. I cannot stress that enough. So the height is 15. Stick that in the formula. Half times 16 is 8. 8 times 15 is 120. So the area of the top half is 120, which means that the area of the bottom half is also 120. So the total area is 2 times 120, which is 240 millimeters squared. Okay, on the home stretch. The last figure before we get into circles tomorrow, actually a couple days from now, the last figure that we need to tackle is the regular polygon. So that's the last thing we have on the page here. We learned in chapter 3, unit 3, that regular polygons are polygons with all sides congruent. So even though it's not drawn to scale, all the sides of this figure are equal. So this is equal to this, is equal to this, is equal to this. So all of these lengths are 5. We also have this measurement from the center of the polygon to the center of a side. That has kind of a fancy name. It's called the apothem. And I forgot to fix my copy before I printed it. So let me make a correction here. That actually should be a 6 instead of a 16. Okay, that makes no sense. That cannot be 16 units long. It's actually 6.0 something something something. It's not exactly 6, but if you round to the nearest tenth, it is 6.0. So we're going to roll with a pretty close approximation. That's called the apothem of the polygon. There's another measurement from the center to a corner, the center to a vertex, called a radius of the polygon, which isn't particularly useful for finding area. It's really from the center to the middle of a side that we need, or that apothem, kind of a funny little name. Now, the trick to getting the area of a regular polygon is to break it up into triangles. So if I take one section, so think of it kind of like a piece of the pie. If I draw in 2 radii from the center to the endpoints of a side, so I'm going to pick this side to which the apothem is drawn. If I find the area of that triangle, then I can find the area of the entire figure, because there are a whole bunch of triangles, just like that one, that make up this polygon. As a matter of fact, there are the same number of triangles as there are sides. So if we can count sides and find the area of one triangle, we can find the area of the whole figure. So the first thing we do is find the area of just one of the triangles. So the area of the triangle is 1/2 times its base. Well, since it's a regular polygon, all of the sides are equal, so this base is 5. So 1/2 times 5 times, and the height of this triangle is the apothem, which is 6. 5 times 6 is 30. Half of 30 is 15. So the area of just this one little triangle part is 15. Well, we have a bunch of those triangles. We have an area of 15 here, an area of 15 here, area of 15 here, 15 here, 15 here, 15 here, 15 here. We have 1, 2, 3, 4, 5, 6, 7, 8 sides for this polygon. So this is an octagon. So the total area is 8 times the area of one of those triangles, 15. So we're always going to multiply the number of sides by the area of one of the triangles to get the total area. So what is 8 times 15? So 8 times 15, we just did that right up here. 8 times 15 is 120. So the total area of the polygon is 120 inches squared. Every regular polygon can be worked this way. Mark off one triangle, find its area, multiply by the number of sides. The only formula you need is the triangle formula. You can survive with the triangle formula for anything other than circles. So it is the must-know formula of the whole bunch. Alright, that's it for today. Next section of your worksheet is the 10-3 practice. So you're going to do all of that today. And we'll start something new tomorrow.